Welcome to the video lecture series on digital signal processing. In this video lecture, we can see about the Z transform using residue method. The residue method for inverse Z transform is the methodology where the concept of complex residues from contour integration is applied. It is usually used when the Z transform is difficult to expand using other methods. So the general formula for inverse Z transform using this methodology is equal to 1 by 2 pi j closed contour integral of x of z power n minus 1 dz. Using the theorem, x of n, that is discrete time sequence, is equal to summation of residues of x of z power n minus 1. So this is the general formula for finding out the uh, discrete time domain sequence using the residue method. The steps followed is, first of all, we have to write what is x of z. X of z into z power n minus 1. Then we have to identify the poles that are available in x of z. So we have to find the residue for each and every pole, and we have to make algorithmic sum of residues into x of z into z power n minus 1. Advantage of this residue method is can be used for higher order rational function, but for smaller things it seem to be a little bit complex. Whereas disadvantage, it's requires some knowledge on the complex variable theory, and it is tedious for repeated poles. So less convenient for simple problem. So we have seen already about the power series and partial fraction method, and the residual method is mainly useful when the function is complex, whereas partial fraction is commonly used method. Power series method, it is used only for small problems, and it is good for educational purpose for learning. Convolution method, it is quite good for product appearance of the given transfer given x of z. So this is about the basic view about the importance of residue method when comparing with other methods. Let us go on with the problem. Use the residue method to find the inverse Z transform of x of z by z minus 2 into z minus 3. So the ROC given is less than 2. So first of all, we have to look into the ROC. It is less than 2, which means that left hand side sequence, and it is non-causal. So we have to the ROC lying inside the circle. For pole for 2 as well as 3 is lying inside the circle. So what we have to do is both are considered as left hands. Both the poles will contribute to the left hand side sequence. So if you draw the circle, ROC is lying inside the circle. So inside the circle is ROC. Okay, so if you look into the circle, it is inside the pole 2, it is inside the pole 3. So both are having the left hand side sequence, so we have to put minus for both the cases. So what we do in this particular problem is we take it as common at the beginning. So x of z is z by z minus 2 into z minus 3. So z per n minus 1. So for pole 2, it is z is equal to 2. Similarly, for pole 3, we have to find the residue. X of z is written as such into z power n minus 1. Substituting the value of 2, we will get minus 2 the whole power n. Substituting the value of 3, we will get the 3 power n. So for since it is left hand side sequence, what we do is we multiply with u of minus n minus 1. Got it? The things you have to observe is what type of sequence, left hand or right hand sequence. And if it is left hand sequence, we have to give minus. If it is right hand sequence, we have to give plus. Here, since ROC indicate both the poles are inside, both poles, the ROC lies inside both the poles, we give minus for both residues. So that's why we take it as a common. Got it? All other things you have to, it is easy only, direct mathematics. Coming on to the next problem. Using the residue method, find the inverse z transform of x of z is equal to z by z minus 1 into z minus 4. ROC is less than 1 here again. If you again see this problem, it is ROC is lying inside both the poles. Again, for both the cases, you need minus. So that's why it is made as common minus. The same methodology here, pole 1, we have to find. For pole 4, we have to find the residue. x of z I'm writing as such into z power n minus 1. X of z I'm writing as such into z power n minus 1. So what will happen is, see, this minus is common for both. So this will get cancelled. Here this will get cancelled. Substitute the z value 1 for this equation, you will get minus 1 by 3. Similarly, substitute the value z here, you will get like this. So if you simplify this, you will get, since both the poles are outside ROC, it is left hand sequence and it is non-causal. What we do is we multiply with u of minus n minus 1. Got it? Well, you can take an x of z, which is equal to z by z minus 1 into z minus 2. Here the ROC is between z greater than 1 and z less than 2. It has two-sided sequence. Z greater than 1, z less than 2 is left hand side sequence, z greater than 1 is right hand side sequence. So we have to consider both of them separately. It is not like previous cases. For n greater than 0, the pole is 1. So while substituting the pole 1 for finding the residue, we have to make it positive. Here, positive sign. So when we cancel this, this will go and we'll get minus 1 at loss. So since it is a right hand side sequence, you have to use u of n. Got it? But pole 2 contribute to the left hand side sequence. So while using it, what you have to do is, while finding the residue, you have to put minus, and at last you have to multiply with u of minus n minus 1. This is the only thing you have to remember always while you are going for final answer. So the answer for this is minus u of n minus 2 per n u of minus n minus 1. Always remember, for a positive right hand side sequence, make it as positive residue and you have to multiply with u of n, minus 1 into u of n. So minus u of n. For negative side sequence, that is left hand side sequence, for finding the residue of that particular pole, you have to multiply with minus and u of minus n minus 1. Similar to the methodology that you use in partial fraction, here also you have to follow the same.